Hello, I'm Chris Seaton. I work at Shopify. I work on RubyConf, which is an implementation of a highly optimizing Ruby compiler built on the Graal VM and some cool technology known as self-specializing AST interpreters and partial evaluation. I've also worked in the past on another Ruby compiler called Rhizo, which is a just-in-time compiler built into MRI, and I maintain the Ruby bibliography, which is a list of academic writing on the Ruby programming language at rubybib.org. It's a lovely autumn day today here in Cheshire in the United Kingdom. I'm sorry I can't be with you there in Denver. I'd love to have heard about what you're working on and show you what I'm working on. I want to talk to you today about compiling Ruby and give you some thoughts on the history of compiling Ruby and what we've tried in the past and what people are trying at the moment. People don't think of Ruby as being a compiled language. We normally talk about the Ruby interpreter. But it turns out there's been a huge amount of work on compiling Ruby over the years, and people have tried some really interesting and diverse approaches to compiling Ruby. And I think it'll surprise you how many Ruby compilers there are. We can learn quite a lot about compilers just by looking at Ruby because of this diversity in different approaches. So even if you just want to focus on Ruby, you can learn tons about compilers. And even more interesting than that, it turns out we can learn quite a lot about cutting edge compiler research just by looking at Ruby. Quite a lot of people have taken ideas in Ruby research over the last couple of decades and tried applying it to Ruby. So if you want to know about what people are trying in compilers in academia, again, we can do that just by looking at Ruby. Looking at Ruby compilers. So what do I mean by a Ruby compiler? For my purposes, I mean something that goes from Ruby source code to native machine code, which can really run on your processor in your machine. Now that could be via some sort of intermediate system, so some sort of library or other system that generates that machine code on your behalf. But the point is it needs to go all the way down to generated machine code. So in this talk, I'm not including things like Yarv, which is a compiler to Ruby bytecode that is then interpreted, and that's how MRI works. Now this compilation could be done ahead of time, such as a traditional compiler for a language like C, where you give it a file and it generates an executable for you, or it could be done just in time, so being compiled as your program runs, such as, for example, Java and the JVM traditionally do. Now, it requires some judgment on my behalf and some opinions to interpret all of these compilers and to categorize them and to say something about them, but I'm not trying to gatekeep what is a compiler. I'm also looking at quite a lot of other people's work, and there's a lot to filter through, so apologies if there's any errors or omissions when I talk about something that someone else has done. Now, did you know there's been at least 25 different attempts to build a Ruby compiler? I was amazed when I found this many compilers when I started digging around, and I think anyone in the Ruby community would struggle to name these 25 compilers. So there's something anyone can learn by looking at this list, and it's really more than 25 because of some of the Ruby compilers have tried different approaches through the years. So especially JRuby and Rubinius have tried a couple of approaches to compilation. So we could count those as separate compilers and get to an even higher number. But it's extraordinary that so many people have tried different ways to build Ruby compilers. Why is it worth looking at Ruby compilers? And why is it worth looking at compilers at all? Well, I think compilers are fascinating. I've been working on them for a couple of decades. And I think one of the great things about compilers, you can talk to anyone who's a developer about compilers because we all use compilers. So everyone's got an opinion on how the languages should be designed, or whether the compiler should run faster, or should it produce faster code after it's run? Should it take less memory? What's important? You can have a conversation with anyone at any level about compilers. And compilers are just really fun. They may seem like a deeply technical topic, but they're conceptually fairly simple. They take a file as input, they do something internally, and they produce a file as output. So that means I think they're fun and easy to work with and easy to understand and to experiment with. And it's surprising how many there are for Ruby. Why has this happened? Why have we managed to get such a huge number of compilers for Ruby? Is there anything special about Ruby that's caused that? There's new interesting compilers for Ruby at the moment. So a just-in-time compiler was added to MRI for 3.0, and Shopify just added in a new one for the next version of Ruby. There's RubyConf, there's JRuby. There's quite a lot of interest in compilers. People are talking more about compiling Ruby these days. So it makes sense to look back over the history. There's lots of interest, lots of existing work to learn from here as well. What's been tried before? Why didn't that work out? What hasn't been tried and what could work out therefore? It's good to look back over what people have tried in the same field as you. I think it's really fascinating that we can trace compiler research through Ruby compilers. So you may not think of Ruby as being a particularly academic language with not a lot of academic interest, but actually you can see a lot of people trying high-level research ideas just by looking at Ruby compilers. Finally, some of the projects which I'm cataloging in this project were at risk of being lost to the mist of time. So to get at least one compiler working, I had to ask one person to get a hard drive out of their attic and to dig out some source code that probably would have been lost unless I'd done it reasonably soon. So I think it's important to archive these compilers and bring them all together. What we're definitely not doing here is talking about which compiler is better or why, and we're not benchmarking the compilers or doing a competition or a shootout. It's inevitably going to contain a few opinions, but I'm trying to be fair and objective about these compilers. So this is the big list of the 25 compilers. Obviously, I'll break this down just as we go through the presentation, but it's great to put them all at screen at once. So for each compiler, I have its name, how long it's been active, whether it runs on top of MRI or some other virtual machine. Does it run just in time or ahead of time? What's the general approach it uses towards compilation? What does the front end work? The front end is the part that takes it from source code. What kind of interpreter does it use? If it uses an interpreter to support the compilation, what kind of data structures does it use, and who worked on them? But that's such a huge list, so let's break it down a bit and talk about the really key Ruby compilers. So the key Ruby compilers in use today. There's JRuby. This is Ruby built on top of the JVM. It compiles down to machine code via JVM bytecode. And JRuby is almost certainly the most deployed Ruby compiler there's ever been. People use it in production, and people are using the compiler part in production. It's a very long-standing project, very stable. It's had a compiler for a very long time. Beyond that, there's RubyConf. This is Ruby built on top of the GraalVM. It has a core built in Ruby, but the rest of it's implemented in Java. And this compiles down to machine code via Graal intermediate representation. There's JRMJIT. This is the compiler which shipped with Ruby 3.0. So Ruby 3 times faster in Ruby 3. That was down to JRMJIT. I've given it a slightly more explicit name of JRMJIT to differentiate it from some other compilers, which we'll mention in a second. There's YJIT, which is Shopify's new JIT for MRI, which should be in a release soon. And there's Sorbet compiler. This is Stripe's Ruby to C extension compiler. And these are the key compilers which I think have at the moment have a realistic expectation of possibly being used in production, that have a team behind them, that are being properly supported by someone, and that are a key effort going forward. Unfortunately, we've lost some Ruby compilers over the years. Some projects have been tried and have sort of died away. Key one is Rubinius. This was Ruby in Ruby, although really much of the VM and all the compilers written in C++ rather than Ruby. And this used LLVM, which is a framework for developing compilers in order to emit machine code. Topaz, this is Ruby implemented on top of Python. So have you ever heard of the PyPy project, which is Python implemented in Python with a just-in-time compiler? This used the same system, but implemented Ruby on top of Python rather than implementing Python on top of Python. This used a technique called meta tracing, which we'll talk about in a bit. Unfortunately, this project's discontinued. There's IronRuby, which is Ruby in C# on top of the .NET ecosystem. And from a couple of years ago, there's Ruby plus OMR. This is Ruby on top of IBM's JVM called the J9, and it reused components from J9 within MRI to build a JIT. And unfortunately, all these projects are dead or stalled for a pretty long period of time. I'd put out some fun niche compilers as well that I'd recommend looking at. Hotstats is a compiler directly from Ruby to ARM machine code. It's very easy to understand, so if you want to look at compilers at the most basic level, you could look at Hotstats. There's Hyperdrive by Jacob Matthews. This is Ruby with a tracing compiler. We'll talk about that in a minute. There's Natalie, which is Ruby to C++. This has a great set of videos on how it works. And there's RubyX, which is Ruby to ARM machine code again, but with a more advanced architecture. So we can split the compilers up into those kind of groups where we have the more serious compilers that are still being worked on, compilers from the past, and some fun niche demos and toys and experiments. This is the timeline of Ruby compilers. It goes all the way from 2004 up to the present day in 2021, with RubyConf being the earliest compiler and Tendergit being the most recent compiler that I could find. I think there's three sort of epochs that happened. So around 2007 there was a large flurry of compilers being implemented around 2007 here. So we had Hotstats, Ludicrous, Maglev, that's Ruby on top of Smalltalk, Rubinius, Ruby.net, Yarv, to LLVM, and MacRuby all started around this time. And then we had a second wave, which is around here, around 2017. This is the start of the lineage of the compiler we have in MRI today, Yarv MJIT. And then around 2020, 2021, we had another sort of flurry of new compilers being added as well, with YJIT and Sorbet. Some of these compilers have died out over time, but some of them kept going for a very long time. So JRuby's been going all the way from 2006 to 2021. The JRuby project itself is older than that, but this is when the compiler was starting to be added. Some of these compilers form family trees between themselves. So for example, Rubinius and JRuby were two projects in their own right, but work was taken from them and integrated into TruffleRuby. So from Rubinius, TruffleRuby takes the core library implemented in Ruby, and from JRuby, TruffleRuby took the parser, encodings, regular expressions, and quite a lot of other work actually to produce TruffleRuby. So these three together form this kind of fork shape. Unfortunately, Rubinius, the compiler, is no longer maintained. LLRB was one of the first more serious efforts to build a Ruby just-in-time compiler inside MRI. That prototyped some ideas, but they then fed into YarvJIT, which is now what we have today. RTL MJIT was the first version of MJIT, used a different architecture to RVJIT, but both of these generate C code as their backend. So we can say that RTL MJIT fed into Yarv MJIT. LLRB and RTL MJIT are now discontinued, but the author of RTL MJIT is looking at building another just-in-time compiler with MRI possibly called Mir MJIT. He's implementing a new compiler system called Mir, which could be used to build a new compiler in MRI. So we have these family trees of these compilers, and they're connected as well. Now to get a better understanding of the space of these compilers, we can divide them up into groups. So we already talked about some of them which are historical and some of them which are still active. So if a compiler hasn't had any work for a couple of years, I'd call that historical, and those which are still being worked on now, we call those active. There's a very large number that aren't maintained anymore, but there's actually still quite a large number that's still being actively worked on today. We can also separate the compilers into whether they are ahead of time, which we said is like a traditional C compiler, or just in time, which is as the program runs. Now most Ruby compilers work just in time, and that's because Ruby is a very dynamic language, so it makes sense to try and run it as the program is running, so you can observe how the compiler is being used in reality, rather than trying to have to guess everything up front, which is what the ahead of time compilers have to try and do. So these give you an executable, which is often a standalone executable, or in the case of something like Sorbet, it gives you a C extension which you can plug into MRI. And these are like a runtime which you run your Ruby program on. Some of them sit in the middle. So MacRuby allows you to either compile ahead of time or compile just in time. JRuby is generally more of a just-in-time implementation, but it's had some architecture over the years to compile ahead of time as well. That can be a case of just putting the program into an executable, or it can actually mean generating JVM bytecode ahead of time. So those two sort of sit in the middle. We can also divide the compilers up between more serious implementations and more demo implementations. I'm not saying anyone's compiler isn't a serious compiler, but I mean those compilers which are part of a dedicated effort from a team to try and do something which might be able to run a lot of Ruby code. So Rubinius was run in production by a lot of people for a long time. JRuby is still run in production by people today. Stripe have Sorbet in production, and the others are all intended to be used in production at some point. We can also divide our compilers between those that are built on top of MRI being the standard implementation of Ruby, and we can talk about those that run on top of a custom VM. So the ones on the left modify MRI to include a just-in-time compiler or some other form of compiler, and the ones on right are sort of re-implementations of Ruby. So JRuby re-implemented Ruby in Java, Ruby.NET re-implemented Ruby in C#, Rubinius re-implemented Ruby in C++, in the same way. There have been 4 attempts to write a Ruby on top of the JVM, so on top of the Java ecosystem. So XRuby and JRuby started around the same time with their compilers. Ruby plus OMR reuses parts of IBM's JVM called J9, but uses them within MRI. And JRuby is built on top of the GraalVM, which is a special custom kind of JVM. There's been 2 efforts to implement Ruby on top of the .NET ecosystem, so Ruby.NET and IronRuby. At one point, Microsoft was trying to give a whole ecosystem of polyglot languages on top of .NET. So there was IronPython, IronRuby, and other Iron languages. And that was part of the dynamic language runtime, but that project was discontinued a while ago, unfortunately. Okay, let's do some deep dives into some of these compilers and figure out what they're doing. So we'll start with Hotstats compiler. So this is a compiler from Ruby code ahead of time down to ARM machine code, and we can use these process flow diagrams to understand what these compilers do. Hotstats is interesting because of it's a very traditional linear sort of architecture. So if you don't know much about compilers, you can understand it fairly easily, and you can look at the source code and follow it and understand what it's doing. So Hotstat takes Ruby source code, it scans it, also known as a lexer. So this finds words and punctuation and symbols, things like that in the source code. This produces a stream of tokens. This then goes through a parser, which produces an AST, so that's an abstract syntax tree, so that's a data structure for representing programs. Goes through a preprocessor, which sort of tries to understand some things about the AST statically. So it looks sort of before and after parts of the program and figure out how they're going to be used and where they came from, things like that. And then it goes into a generator, which generates machine code. And it talks to a register cache in order to do that. Registers are bits of memory inside your processor hardware that can store values. That generates assembly code. So assembly code is the textual version of machine code. And then the system assembler and linker runs to produce an actual executable. So it's a pretty straight line through the system. And it uses just one data structure, the abstract syntax tree, to produce machine code out. So Hotstat is the simplest kind of compiler. And it's very easy to understand because of that. Rubinius is a particularly fascinating Ruby compiler because it was a complete re-implementation, and they tried many different approaches to compiling Ruby in Rubinius over the years. Rubinius doesn't contain a just-in-time compiler these days, and the project seems to have stalled entirely, unfortunately. But we can look at the Rubinius just-in-time compiler as it was the last time it shipped with a just-in-time compiler. Now this is starting to get much more complicated. And this is typical of compilers. There's a simple sort of starting point for how compilers are designed, and then you can add more and more things to make it more complicated and more effective and more optimizing. So in Rubinius, you have your Ruby source code. That's lexed in the same way, which produces a stream of tokens. That's then parsed, and this uses a sub-project of Rubinius called Rubinius Melbourne. This produces a C++ data structure that is an abstract syntax tree. And that's then converted using another Rubinius library to a Ruby data structure. And that's then compiled, but we mean it's compiled down to a bytecode. So this gives us a bytecode format like Yarv's bytecode. This then runs in the Rubinius interpreter. When a method's been called a certain number of times, it reaches a compilation threshold, and this means that it's realized that the code is hot enough to bother compiling. And then it asynchronously starts the compilation process. So this is the actual just-in-time compilation process from here. So it gets translated to LLVM IR, which is a version of, it's like a pseudo machine code. This talks to some processors such as the inliner, which takes methods that are called in the Ruby code and inserts them, their bodies into the call site directly. And then it runs a series of LLVM optimization passes. So these are provided by LLVM. And then there's some custom LLVM passes as well. So the Rubinius team extended LLVM to write special optimizations which understood how Ruby worked and therefore particularly useful for optimizing Ruby. That then is generated to machine code by LLVM, and that installs code within the process so it doesn't go out on disk, it simply lives within memory. And then if the optimizations prove invalid, it can de-optimize back to another interpreter and then back into the main interpreter. This special interpreter here is designed to recover from code needing to be interpreted again because the compiler wasn't able to handle it. JRuby is a very fascinating compiler to do a little bit of a deep dive into as well. JRuby has a huge number of tiers. So a tier in a compiler is a different state that your program can be in. And because of the way JRuby is built on top of the JVM, but also with its own representation for programs called their own IR, there's a huge number of phases that JRuby passes through. I'll divide this diagram into two to make it a little easier to understand. So in the same way, JRuby takes your source code, it lexes it, it parses it, and then it generates its own data structure that's not an AST, that's like a pseudo machine code called its own IR. And that represents your Ruby program. This then goes into a startup interpreter, which is a simple interpreter for that IR. And that itself is subject to JIT compilation. So that startup interpreter can be in one of 5 distant tiers itself while it's running your program. There's then a threshold for compilation, like in Rubinius, which means if it's called that many times, it will decide that method is hot and they'll start to go and compile it. And again, that's asynchronous. This happens on a background thread. What happens is we build a data structure called a control flow graph. So this understands how the code in your Ruby program runs through different branches and do different loops. They then run a series of their own optimization passes, which they've built from scratch within JRuby. There's a mechanism for inlining, which is disabled at the moment. And there's also some very advanced optimizations, such as unboxing optimizations, which are disabled by default in JRuby. That then goes to a system which generates JVM bytecode. This is then passed into a class file. It's called a file, but it's in memory. This generates a JVM class file. So what we've now gone through is we've gone from your Ruby code through JRuby's data structures into JVM bytecode, and then that gets passed into the JVM. So your bytecode, which was generated from your Ruby code, then goes into another interpreter. And then it's subject to a threshold to be compiled into actual machine code by one of the JVM's JIT compilers. And the JVM has 2 JIT compilers, but it runs them in 3 different configurations. So the simplest compiler, called C1, that is another threshold, and that decides to then run in C1 with extra profiling, so to gather more information. That generates machine code. Then if that's called enough times, it gets compiled again, and it goes into the C2 JIT compiler. This is the top tier of compilation, which generates machine code. And at any point, if it decides it's got something wrong, it can de-optimize out and come back into the bytecode interpreter. And this all adds up to JRuby having up to 9 tiers of compilation to optimize your Ruby code as effectively as possible. Now, we said we could track compiler research through Ruby. So there's been some big ideas in in compilation over the last couple of decades, such as tracing, meta tracing, lazy basic block versioning, self-specializing ASTs, and partial evaluation and the future mirror projection, which we'll go through. So tracing, this was a research idea for originally a language called Dynamo. There's a paper written by Sullivan et al. The idea is that you monitor what instructions you're running when you run your Ruby program, and then you generate machine code for those instructions. And this is being tried in a JIT called Hyperdrive today by Jacob Matthews. Beyond tracing, there's an idea of meta tracing. The idea is that you trace the code which implements an interpreter. So you write a simple interpreter in a language like Python or Ruby or Java, and then you trace the code behind that interpreter and generate a compiler from that automatically. So this is what PyPy does. This is a research idea applied for Ruby in the Topaz JIT by Alex Gaynor and others. Lazy basic block versioning is an idea where you have a wavefront of your code running through basic blocks, which are little snippets of Ruby code that don't have control flow in them, and you generate a machine code version of each of those basic blocks. And this was a research idea being applied for Ruby today in YJIT by Maxime at Shopify and others. Self-specializing ASTs. This is an idea that programs should specialize themselves as they're running, so they replace little parts of themselves with more efficient versions as the program is running. And this is an idea being applied for Ruby in TruffleRuby by myself and the rest of the TruffleRuby team at Oracle and Shopify. You can see the paper here for this on rubybib.org. Partial evaluation is also a technique that's used in TruffleRuby. The idea is that we can take an interpreter for a language and automatically produce a compiler for it by executing as much of the program as we're able to while it's being compiled to get a smaller equivalent program. And again, the paper for that is on rubybib.org. Partial evaluation was described by Tom Stewart at a RubyConf talk in 2013. Tom described it in the abstract, and now it's being applied for real in TruffleRuby. So the themes to ruminate on. Something people often try or have been trying for many years with Ruby compilers is to try to do as much as possible automatically. So rather than trying to manually generate machine code for every part of Ruby, a lot of people have tried automatically generating Ruby compilers. That's what Topaz does with meta tracing. It's what TruffleRuby does with partial evaluation. Rubinius tried several ways to get a compiler from the interpreter automatically. I think that's really key for maintainability, to try and get one code base that everything comes from. Where might you need to go next? Something that people have tried pushing towards with Ruby compilers over the years, having some sort of data structure to represent Ruby programs. This is the data structure that TruffleRuby uses, which is probably the most advanced. JRuby has their own intermediate representation as well. If we have a more advanced data structure for represented Ruby programs, we can do more advanced optimizations with them, because we're more free to understand what the program does and why. And if we generate richer data structures with more information, I think we can do better optimization, and I think that's where Ruby compilers are going to go in the future. What might we need to do next? Polyglot compilation. So something interesting that TruffleRuby is trying is it's using a compiler for regular expressions as well as for Ruby and combining them together. And Oracle have got fantastic speed up results from combining a JIT for regular expressions with combining a JIT for Ruby. And we could do the same thing possibly with combining JavaScript and SQL and other languages like that within one JIT. If you want to know more about compilers, there's loads of talks you can catch here at RubyConf alone, which I think tells you something about how popular Ruby compilers are becoming. There's a talk on YJIT. There's a talk on JRuby. I think it's a general JRuby update, but it probably talks about the compilers as well. There's a talk about the Yarv MJIT. There's a talk about TruffleRuby and compiling regular expressions. There's a talk about the Sorbet compiler, and there's a talk about TenderJIT. So if you want to know more about Ruby compilers, there are tons of opportunities here at RubyConf. And if you want to watch and read some people to learn about Ruby compilers, I can recommend Tim Morgan, He live streams his Natalie Ruby compiler on YouTube. Vidar Hogstad, he's got a 45 article blog post series about his Ruby compiler, which is very understandable. I'd recommend people start there. And Aaron Patterson has been live streaming him working on his 10-digit compiler on YouTube as well. Why Ruby compiler is so cool? You can build one yourself. We can see that from the number of how many people have tried to do one. There's so much freedom for how to design and architect them. There's so many different things you can try. There's tons of open space for new ideas. If you've got a big new idea, you can try it and experiment, and you might come up with something completely new. You can apply research, as we've seen, pick up a paper on compilers and see how to compile it, how to apply it to Ruby. And it's a really active area. There's so many compilers which are still being worked on today. I've written up this survey of compilers on RubyCompilers.com. I'm calling it the Ruby Compiler Survey, and this is where I'm also archiving all these old compilers we'd like to keep forever. So if you want to know more about what I've taught today, go to that project. And as I said, I also maintain the Ruby bibliography at rubybid.org, which is a list of academic writing on Ruby. I'm Chris Seaton. Please reach out to me on Twitter if you want to know anything more about Ruby compilers. Thanks for listening.